Now here, this circuit shows the common emitter configuration. This circuit shows the common emitter configuration. Already I explained what are the input voltage, input currents, output voltage, output currents in the case of common emitter configuration. Once again, I am explaining this. See here. Here, first we have to draw this NPN transistor symbol. Here, emitter is connected to the ground. In the case of common emitter configuration, emitter is connected to the ground. Okay, here this RB is called your current limiting resistor. To avoid the damage of the transistor, we are going to connect this current limiting resistor RB. Why? Because the input is base, so that's why I'm going to mention this as RB, R suffix B. Okay, this is a current limiting resistor RB. Okay, one second. Now, sir, first we are going to draw the NPN transistor symbol, and after we are going to draw this current limiting resistor. Okay, and in the case of common emitter configuration, emitter is connected to the ground, and output is collector. Okay, at the output side also, I am going to connect the current limiting resistor, that is RC, and representing it as RC. Okay, now in the case of common emitter configuration, we are going to connect the circuit in active region. Right? Because in the case of active region, the transistor is going to act like an amplifier. In the case of active region, emitter is forward bias, collector junction is reverse bias. Now here we are going to connect the collector junction in reverse bias. Okay, if you want to connect it in reverse bias, here this terminal is connected to the positive. Why? Because this is a collector is your N terminal. This is an NPN transistor, na? So this is an N terminal. Now when is connected to the positive? Here we are going to connect the positive. Now here this is a supply voltage. Here N connected to positive. Now this is connected in reverse bias, and after emitter connected in forward bias. That means here this is connected to the positive terminal, negative terminal. Now here, okay, here emitter terminal is connected to the negative of your battery. Emitter is connected to the negative of your battery. Now this is connected in forward bias. This is connected in reverse bias. Okay. Now representation of your current. Here emitter current is away from the transistor. If you observe here, emitter current is away from the transistor. That means IB/IC must be entering into the nodes here. IB is entering into the transistor. IC also entering into the transistor. Okay. We can explain in this manner. Otherwise, we can explain this current direction by using the supply voltage also. Here the supply voltage is in clockwise direction here. If you observe the supply voltage, this is in clockwise direction from positive to negative. So that's why the IB is in from left to right like this. Similarly, at output side, if you observe here, here it is flowing in anti-clockwise direction like this. So that's why the IC is moving in upward direction. That means right to left like this. Okay. We can explain this current direction by using the supply voltages as well as the concept of IE is equal to IB plus IC. Both are same. Okay. We are going to get the same result. Okay. Now this is about the currents. Now see the supply voltage indications. Supply voltage indicates with VBB, input supply voltage. Here this is connected to base. Input is base. So that's why it is represented with VBB. Output is collector. So that's why I'm representing with VCC. Okay. Now this is your input supply voltage. This is your output supply voltage. Now here input voltage across this base and emitter is given by VB. Output voltage across the collector and emitter is given by VC. Okay, this is representation of your input voltage, input current, output voltage, output current, and supply voltages, input side and output side. Okay, now I'm going to write the KVL equation at input side, similar to your common base configuration. Okay, now here this is in clockwise direction. Here this current direction is in clockwise direction. Now this is your voltage, right? Remaining two are the voltage drops, and remaining two are the voltage drops. So that's it. VBB is equal to IBRB plus VBE. Here, VBB voltage, right, is equal to the IBRB voltage drop, VBE voltage drop. Okay, why? Because current to the RB is IB. So that's it. Voltage across RB is given by RB into IB here. Okay. Now from this, I am going to write the output current as well as output voltage equations here. Output current is given by VBB minus VBE by RB here. Similarly, in output given by VBB minus VBE by RB. Similarly, input voltage is given by VBB minus IB into RB. So this is our input voltage as well as input current equation. Okay. Now see the output equation. Apply the KVL at output side. Now here VCC is your voltage rise and why? Because here the current is in anti-clockwise direction. Here the current is in upward direction from negative to positive. So this is your voltage rise VCC. Here VCC is equal to voltage up across RC is given by IC into RC. Why? Because current to RC is given by IC. So it is IC into RC plus voltage up across this transistor VCE. So VCC is equal to IC RC plus VCE. Again from this equation, I am going to write the output current as well as output voltage equations here. IC is equal to VCC. If it comes to LHS set, it is VCC minus VCE by RC. Similarly, output voltage VCE is equal to VCC minus RC into RC from this equation. VCC is equal to VCE is equal to VCC minus IC into RC. Now these are your output current, output voltage equation from this output side loop. Okay. In addition to these 4 equations, one more equation we are writing, that is in terms of reverse saturation current. We are going to consider the reverse saturation current in the case of output side. Why? Because the output is connected in reverse bias. Here, the collector terminal is connected in reverse bias. So that's why I'm going to consider the reverse saturation current. Okay, I already explained this equation. Output current is equal to the gain into input current plus 1 plus gain into reverse saturation current. In the case of common emitter configuration, gain is represented with beta. Now here, output current. In the case of this common emitter configuration, output is IC. Now here, IC is equal to gain means represented with beta. Input current. In the case of common emitter configuration, input is given by IB. If you observe here, input is IB. So substitute here IB plus 1 plus gain means beta. IC naught, IC naught. Okay. Now I am writing the same equation as IC plus beta into IB plus ICEO. Here ICEO represents the reverse saturation current in the case of a common emitter configuration. See here this not, this O, this 0, this indicates the reverse saturation current in the case of common emitter CE, in the case of common emitter configuration. This is the representation of reverse saturation current in the case of common emitter configuration. In some textbooks, directly is going to give the equation as like this: IC is equal to beta into IB plus ICE naught. Whereas ICE naught is given by IC naught into 1 plus beta from this fifth equation. IC naught plus 1 plus beta. Now these all are the equations related to common emitter configuration: output voltage, output current, input voltage, input current equations. Okay. Here we are going to draw the characteristics graph between the input voltage versus input current. Here again, input characteristics are drawn between the input voltage versus input current whenever the output voltage is constant. So here, what is the input voltage? VBE. What is the input current? IB. Here, input voltage VBE versus input current IB. Whenever the output voltage VCE as constant. VCE as constant. Okay. Now VCE is equal to some 0. VCE is equal to some 2 or 3 or 4. Okay. That means VCE2 is higher value. VCE1 is lower value. So this is 0. Assume this has some 0 value. Assume this has some 2. Okay. Now, so these are similar to your PN junction rate forward bias characteristics. Okay. Up to some voltage, there is no conduction. Up to the cut-in voltage, there is no conduction. Why? Because here the emitter junction is forward bias. Up to the cut-in voltage, there is no conduction. So that's why it is 0. The current is 0. After that, the current is going to increase. Here also, the current is going to increase. When you increase the output voltage from 0 to the 2, here VC is equal to 0 constant. After that, again, output voltage VC2 is equal to 2 volts. This is also constant. When you increase this output side voltage, the graph is shifted towards right side. Why? Because the output voltage is increased from 0 to 2. This is going to affect this input graph. Now the graph is shifted towards right. Okay, this is a input characteristics. Okay, I'm going to explain this output in my next class.